Welcome to the course Introduction to Mobile Robotics. Today we are going to start with Module 5. In Module 5, we are going to deal how the path planning can be done. After building a map and estimating pose using SLAM, the next question is how does the robot decide where to move? Path planning is the process of computing a safe route from a starting position to a goal position. The robot must ensure that the chosen path does not intersect with obstacles and also satisfies constraints such as minimum turning radius or maximum velocity. If your slide contains a grid map figure, in this figure you can see that the robot's starting location and the goal location. The shaded cell represents obstacles and the free cell represents the navigable space. The planner searches through these free cells to find a connected path that avoids collision. Path planning is not just about finding any path, it often tries to minimize cost, such as shortest distance, minimum time, or least energy consumption. Thus, planning transforms a static map into a feasible trajectory. Now we will see the next topic, that is a global path planning. Global path planning assumes that the robot has already access to a complete map of the environment. In the figure, the environment is represented as a graph. Each cell or node is connected to neighboring nodes. The planner searches through this graph to find the least cost path from start to goal. Algorithms like Dijkstra or A-star evaluate different possible routes and compute the optimal one based on a cost function. Because the planner has access to the entire map, it can make decisions considering the whole environment, not just nearby obstacles. This makes global planning suitable for static environments where obstacles do not change frequently. Global planners generate optimized and smooth paths. If the notice how the path considers the entire environment. It avoids obstacles strategically and often follows the shortest route. However, this approach assumes that the map remains unchanged during execution. If a new obstacle appears that was not in the original map, the planned path may no longer be safe. So global planning provides a high-level route, but it may need updating if the environment changes. Think of it as planning your journey using Google Maps. Before starting, it assumes roads remain open. Local planning focuses on short-term, real-time time decisions. The robot uses sensor data to detect obstacles around it instead of planning the entire route at once. It continuously adjusts its movement based on what it senses. Local planning is reactive. It responds immediately to unexpected obstacles. Unlike global planning, it does not require a complete map. It only needs local sensor information. This makes it very important in dynamic environments where the obstacles may move or appear suddenly. Local planner emphasize safety and responsiveness. The goal acts like an attractive force pulling the robot forward, while the obstacles generate repulsive forces pushing the robot away. The resulting motion is a combination of these forces. Methods like dynamic window approach evaluate possible velocity commands and choose the safest one. However, local planners may sometimes get stuck. For example, in potential field methods, the robot may reach a local minimum where forces balance but the goal is not reached. So local planners are adaptive but not always globally optimal. Now we'll see the difference between the global and local planning. At the figure shows a comparison between the two types of planning. At the top level, the global planner computes the overall path from start to goal using the map. Below it, the local planner refines that path by generating velocity commands based on real-time sensor data. Global planning gives the answer for what is the best route overall. Local planning answers how should I move right now. In practice, both planners work together. The global planner gives direction, the local planner ensures safety and feasibility. This layered approach is standard in robotic navigation system. First, the robot builds a loads or map. Next, the global planner computes a path. Then the local planner converts a path into velocity commands. Finally, the locomotion controller executes those commands through wheel motors. This shows how planning connects high-level intelligence with low-level motor control. Notice how all modules we studied, SLAM, Kalman filtering, locomotion control come together here. Path planning acts as a decision-making layer between perception and control.